Today we're going to be talking about image classification, and in particular a specialized architecture for image classification known as convolutional neural networks. We'll start by looking at why a simple feed-forward neural network, which CNNs are, but they have a particular structure, why this generic feed-forward structure is not sufficient. Then we'll look at key parts of CNN architectures, convolution and pooling, how they operate, what their function is, and with some examples. All right, so just to remind what the problem is, we are getting images here, maybe high resolution image. We have to learn to map that to a category such as mushroom, and we might have, say, 1,000 different categories. So this is a multi-way classification problem where the input example X is an image and the output is a category Y. So let's try to see why we are not using feed-forward neural networks for this purpose. Here's the input image again. Let's say for simplicity that it is 1,000 by 1,000, so not very high resolution image. So it has 1,000,000 pixels. Okay. We're going to then apply a single hidden layer to this image, a layer that may also have, say, 1,000 by 1,000 units arranged in such a way that each pixel looking thing here is a single unit that takes the image as an input as before. Okay, so now we will have a fully connected mapping here with some weight matrix W that will be now million by million. Okay, because there are 1,000,000 pixels and each unit here has 1,000,000 weights associated with it. A different unit right next to it has a different set of 1,000,000 weights corresponding to the image, and so on. All right, so that's a trillion weights, so a good fraction of the connectivity of the brain would actually go into this single input to a first layer of neural network transformation. Okay, that would take a lot of images to actually learn with any confidence the actual values for those weights. So that's problem number one, just the number of sheer number of parameters that we would need. Okay. Problem number two is a little bit more subtle, but let's look at it this way. So here, if I'm looking for mushrooms, here's a mushroom. So if all the training examples that I see have mushrooms here in the center, okay, then comes a test example where the mushroom is moved slightly to the side here. Would our neural network classify that mushroom correctly? No, it would not, because any weights emanating from the pixels here would never have seen the mushroom, so they would never have learned to classify such examples correctly. Okay, so we are introducing too many degrees of freedom, and the same object that appears in slightly different location would have to be learned anew with weights that emanate from that part to recognize objects that we want. Okay, that's problem number two. Okay, so what can we do? So let's take a very simple unit here. We can certainly effectively classify little patches of an image. So here I'm going to draw just an 11 by 11 pads. So again, it has pixels as before. And a single unit here that takes that pads as an input and produces an output, and now has some vector of weights associated with that unit. Okay, so I will have a weight here, single weight corresponding to each of the pixel in this little pads. Okay, so the dimension, in the absence of offset parameter, the dimension of the weight vector here would be 121 or 11 times 11. Okay, we can certainly efficiently train such classifiers, a small number of parameters, 121. We don't need that many patches to actually learn effectively what that weight should be. Okay, so let's cast this unit slightly differently. Okay, now we know that we have a weight corresponding to each pixel in the image. So in that sense, the weights can also be arranged as a matrix of the same size as the input image. So weights can also be turned into 11 by 11 grids. Okay, here I have a particular chosen weights. So this is now the W and that we have 121 coordinates, where each pixel in this image, its value corresponds to the associated weight. Okay, and here I have just an example 11 by 11 input, corner of that mushroom. Okay, here's this is the input example X. Okay, so how this unit here would operate is that we take an inner product between these two matrices. That just means that we vectorize the matrices and take a normal inner product. Or alternatively, you can think of it as taking each pixel, multiplying with the corresponding weight pixel at a time, and so adding them up. We get one real number. We pass that through a non-linearity, such as the rectified linear transformation, and that gives us the output F. Okay? So looking at it this way, we can think of the weights as actually an image. It is the image that the classifier here, or the unit, prefers to see. Just as before, in terms of a linear classifier, if the input example X looks like the parameter vector, you get a large response here. And the same is true here. If the image looks like the parameter pads here, then we get a large response, otherwise not. All right, so now we have a little pads unit with weights that equal to the number of pixels in the pads. All right, so how can we use that classifier now to effectively generate that layer 1 transformation? Okay, we are only going to be using these weights. So the weights in this transformation from the original input image to this feature map here, the layer 1 units, again, there are exactly the same number of units here as there are pixels in the original image. But what we're going to do is we're going to take those 11 by 11 patches here. Okay, that's now the input to our little classifier, and we use the same weights here. So the same image pads, compare it to now the pads in the original image, pass it through a rectified linear unit, get a real number, and put that number in the feature map here. Okay? Then we move to a second unit here, move the pads slightly. Okay, here with one pixel, but it could have stride, that is, it could move a couple of pixels at a time. Now we get a new pads as an input, apply the same weights here that we have, get a real number and put it there, and so on. In each location we have a pads, we run it through the classifier, we get a corresponding value in the feature map. Okay, so now I have defined a layer 1 transformation that's extremely efficient in terms of the parameters. Okay, So if we are looking for edges of this kind, and we pass that paths here, then we might get a high value in locations where such features appear. So we would get a high values here. Okay. So now the transformation from the input image to a feature map here involves only 121 parameters. Okay. But we get a feature map where each location here, each activation of the units, tells us how much that feature is present in the corresponding location. Okay? So let's compare this to the simple feed-forward transformation. There are two differences here. First, each unit here connects only locally. Okay? So it doesn't look at the whole image, it only looks at the paths. That's difference number one. The second difference is that the weights that are used to transform each activation here, each paths into an activation in a feature map, uses the same set of weights. Okay? So we have local connectivity, that's number one, and number two, we have shared weights. Those are the two differences that we now have. This is now something called a convolution operation. Applying this little classifier throughout the image, get the activation values as another image, which is just a something called feature map. All right, so let's see how this actually works. Here I have now a little pad that tells me the weights, W. Okay, and now I take that size pad, I apply it throughout the image. So this is what it would look like applying that filter through this image, getting this feature map as a result. All right. Now, the second thing that we wanted to do is something called pooling. And that just means that we want to start separating what is in the image from where it is in the image. So we might want to recognize objects and features in the image, but forgetting exactly where it appeared. If our ultimate goal is classifying the object regardless of where it appears in the image. This is facilitated by an operation called pooling. Okay, and it's a simpler than convolution, but it is applied in a similar fashion. I again have a little pads here. Now has it's a 5 by 5 pads, so it has 25 pixels. And all I'm going to do is to store in the corresponding location in the resulting map the maximum value of these 25 pixels. So I take the values of those pixels, 25 pixels within that pads, and I'm just taking the maximum value. So maximum activation of what that feature was trying to detect. So I'm going to store the fact that there is activation, but not where it is among those 25 pixels. Okay? So typically there's some stride here. So for example, stride 2. So I move the paths 2 pixels rather than 1 pixel. As a result, I will get a smaller map here than the original image. If the stride is 2 in horizontal and vertical direction, then the image that I get has 4 times less pixels. Okay, but each location here corresponds to the maximum value of the 25 pixels that it is looking at in the original image. That is a pooling operation. And just to illustrate, if I do that pooling operation for a feature map like this, I get a smaller map here that might look like this, where each location now tells me how active, how much activity there is in the feature map in the associated paths location. Okay, so resulting pooled map here starts forgetting where the features appear, but still maintaining information about the fact that they are there. All right. So let's look at how to then actually construct a convolutional neural network. I will take input image here. And now, since each convolution corresponds to some weight matrix here associated with the little paths that I'm looking at, it corresponds to looking for a particular type of feature, like an edge here. But that's not the only kind of feature that I want. I want to find a feature of a different diagonal edge, vertical edge, horizontal edge, or some combination, and so on. So I'm going to map the original image into multiple feature maps, where each feature map is generated by a little weight matrix, the filter, also called a kernel, that defines the little classifier that's run through the original image to get the associated feature map. Okay, so I get multiple feature maps. Then I might run a pooling layer here that reduces the sizes of the images, and so on. So each of these feature maps defines a channel for information, okay? And I might pool within the channel, expand further into now other features that are run on top of the pooled image, and so on. Okay, so I can combine these convolution looking for features and pooling, compressing the image a little bit, and forgetting the information of where things are, but maintaining what is there. Okay. So here's an illustration of an actual architecture that was the first neural network, fully neural network, end-to-end learned neural network architecture that won the 2012 ImageNet competition. Okay, so it has initially here 96 different little classifiers, 96 different feature maps. And each feature map is constructed by 11 by 11 filters. Okay, so you get an original image, you run these little classifiers, you have 96 different classifiers, you get 96 different feature maps. Okay, then you do just a tiny bit of image processing, normalization, apply the pooling result followed by convolution, and so on. Okay. So you get here an image, it's mapped through these multiple layers, and finally mapped into classification probabilities for getting a particular label 1 out of 1,000. Okay, so this is a feed-forward architecture, but it's highly structured in terms of these efficient layer-by-layer transformations via the convolutions and pooling. Okay, the parameters of this model are learned exactly as before, end-to-end, by getting a target label, back-propagating the information now in a structured way because our architecture has shared parameters and is parameterized more efficiently, all the way back to the first image transformation. Okay, so conceptually, training is as before, using stochastic gradient descent with a few tricks based on getting pairs of image and the corresponding label. All right, so how does it work? Here are examples of this model run through actual examples, and you get these bars here that specify the probabilities that the model thinks it is a particular category here. All right, the pink value here is the correct category. So here the correct category is the container ship, and it is the first one, and so on. Okay, here are just some examples where it makes an error. For this image, the model predicts with high probability that it's convertible, but the actual answer in the data set for that image is squirrel, and so on. So it works quite well and makes actually quite reasonable errors, as you can see here. All right, so let's just finally look at an example of the type of filters that we get as a result of training such a CNN architecture. So remember, in this model, original image was initially expanded into 96 different feature maps, and each feature map corresponds to a filter. So a little pads, 11 by 11 pads. It has color dimensions as well, so it's actually a cube rather than just a square pads. But if you think of it as a square pads here, it's a little image, and now that little image tells us what that filter would maximally respond to. So what kind of image would it like to see for it to activate the corresponding location in the feature map? Okay, so you can see that there are filters that look for edges of various different kinds, horizontal and vertical ones, and then there are some color units and so on. Okay, so none of these were specified ahead of time. They were all learned from random initialization by just having the input image and the corresponding label back propagating the information to these little feature classifiers and adjusting them accordingly. Okay, so the take-homes for this lecture are to understand what a convolution operation is, that it's an efficient transformation relying on these little paths classifiers that are run through the image generating a feature map. Second thing is the pooling that tries to generate a slightly more compressed image for getting where things are, but maintaining information about what's there, what was activated. Okay, and CNNs are architectures that combine these type of layers successively in a variety of different ways.